Okay, so in this review session, we're going to go over some commonly missed exam questions. So like I've said in past videos, there's all the different versions of the first three exams are all on Blackboard. So I just pulled some of the most commonly missed things or question types that weren't on the review that we've been going through to just have a session about those. So in the final review sessions we've already had, we talked about writing a number in a base other than 10 and writing that in expanded form and converting it to base 10. You may be asked just to convert something from a different base to base 10. The process for that is writing it in expanded form. But we can also have the situation where we convert things from base 10 to a different base. And so remember that whenever we do that, it's all about division. So I'm going to write in blue. So whenever we're converting 457 in base 10, so a number in base 10 to a different base, we're going to divide by whatever our new base is. So whenever we do that, we take 457, oh, sorry, 457, there you go, looks nice now. And we're going to just divide it by 8. So remember that whenever you do this, you just kind of keep dividing by what your new base is until you can't anymore. So whenever we start out, 8 can't go into 4, but 8 can go into 45 5 times because 5 times 8 is 40. And we have 5 left over. We bring down the 7. 8 goes into 57 7 times because 7 times 8 is 56. And then we have 1 left over. So whenever we do this, whatever our remainder is, this is going to always go in our ones place. And I typically have written this as the 8 to the 0 place because it's going to go in our ones place. Our next remainder is going to go in our 8s place. Our next thing is going to go in our 8 squareds place, and so on. So we're going to take this 57, our quotient here, and we're just going to keep dividing our quotient by 8. So 8 goes into 57 7 times because we have 1 left over. And so again, this next remainder is going to be our 8 to the ones place. And then now our quotient is a 7, and that can't be divided by 8 anymore. So once we get a quotient it's essentially smaller than 8, we're going to have our quotient be in the next biggest place. So that's going to be in the 8 squareds place. So remember that whenever we are writing things in a different base, that our lowest place value for every base is always the ones place, or whatever that base is to the 0, because any number to the 0 is 1. So that's the ones place. Our next place value is going to be the 8s place or the B place for whatever base B we're in, right? So typically in base 10, this is going to be the 10s place. And then we're just going to keep going up in powers. So we could keep going up as much as we need to. But our rightmost place is always going to be the ones, and then the base, and then that base squared, cube to the 4th, and so on. So whenever we write this out, in our 8 to the 0, we have 1. 8 to the 1, we have 1. And 8 squared, we have 7. And so that's all we have to do. So 457 base 10 is 711 base 8. Remember, whenever we've gone through this, even though we say 457 in base 10, a lot of times when we're talking in other bases, rather than saying 711, we say 711 because 711 base 8 represents the value 457. Okay, so that's this first one about converting from base 10 to a different base. You essentially just divide by that base until you can't anymore. Are there any questions on how to do a question like this?
Could you go over or at the end maybe number 4, the question that was right before that one, the write in expanded form and convert to base 10, the 354 base 6, if you have time?
Yeah, I can go ahead and do that now.
Okay.
Let me just write. I'm gonna erase this answer so that way I have a little bit more space to do that. So the question that he asked about was the other thing. So writing something in taking a number that's in a different base and converting it to base 10. So rather than doing the question that's on exam 1 version 1, I'm going to go ahead and just convert 711 base 8, if that's okay, and write it and convert it back to base 10. So whenever we're converting something in base 8 to base 10, the first step is always to write it in expanded form. So again, we're going to use our place values. So this 711 base 8 is 1. We have a 1 in the ones place, which is the 8 to the zeros place. Oops, sorry, that should be a plus. We have a 1 in the 8s place, which is the 8 to the 1. And we have a 7 in the 8 squareds place, right? So normally that would be our 10 squareds, but in a different base, it's whatever the base is. 7 times 8 squared. So whenever we write this in expanded form, we write it with this multiplication and addition, and then to convert it to base 10, we just kind of expand everything out using the order of operations. So 1 times 8 to the 0 is 1, it's just 1. And then we're going to add 1 times 8, which is 8. And then we're going to add 7 times 8 squared. So 8 squared is 64. And then if we multiply that by 7, 4 times 7 is 28. So write the 8, carry the 2. 6 times 7 is 42, plus 2 is 44. So that's 448. So then we take the 448 and we're going to add 9 to it. 8 plus 9 is 17. So write the 7 and carry the 1. And so then we're going to get 457. So this is how you convert this number back and forth. So I know I didn't really answer your question. I didn't do number 4 right above this on this version, but just because that one's already written, I felt like we could just do this one backwards. Okay, are there any questions on converting numbers to or from base 10 or just between bases?
So that one you just did, that would be 457 base 10, right?
Oh, yeah. So this is base 10.
Okay.
Thanks. Sorry about that.
Because, I mean, well, you always want us to put in the 10, right? Just to be sure.
Yeah, it's always, I mean,
Okay.
better safe than sorry, right? To
Yeah.
always put what base you're dealing with if you're dealing with different bases.
Okay. All right. Thank you.
Any other questions on this? Okay, so another question that was commonly missed on the first exam was using this partition model. So this is an example of something I've talked about in the other review sessions. If I tell you to answer a question using a specific model or algorithm, you should use it. So we're going to use a partition model. So I know that may have been something that you weren't expecting on the first exam, is that you're going to get points off if you don't solve the question using the method that's stated. So whenever we're using a partition model, this one, we're dividing 15 by 6. So we're dividing 15 things into 6 groups. So we can draw 6 groups. So we're going to draw 6 groups, and then we divide 15. Sorry, this kind of got crooked. It's still kind of crooked, but that's okay. Okay, so we have 6 groups here, and we want to divide 15 evenly among these 6 groups. So when we do this, we just start doing it. So 1, 2, 3, 4, 5, 6. As we're dividing them evenly, we're going to put 1 in each group and then 2 in each group and then see how many we can get. So that was 6, 7, 8, 9, 10, 11, 12. So now I've done 12, so I only have 3 left. So I can't divide 3 evenly among 6 groups. So I'm going to have those 3 out here. So whenever a lot of people did this on the exam, a lot of people put these 3 into the first 3 groups, and then we're like, oh, I can't keep going. So I don't think any way putting the 3 in the groups or leaving them out is any more correct than the other. Either way was fine. So we can have 2 in each group with 3 left over. So then this tells us that 15 divides equally into 6 groups. by having 2 in each group with a remainder of 3. So 2, remainder 3. Yeah, so I think the reason this was commonly missed on the first exam is a lot of people didn't know what to do with the remainder, but just tell me that there's a remainder. Okay, are there any questions about using this model or this question? Okay, so moving on to exam 1 version 2. So we're looking at a sequence again. So I know that we did a sequence on the other review videos, but I just wanted to look at it again. So if we're looking at an arithmetic sequence, so if you remember what an arithmetic sequence is, this tells you that we're going to add. So arithmetic sequences correspond to adding, geometric sequences correspond to multiplying. Then we also have sequences of squares and cubes. And if these words mean nothing to you, I would recommend going and looking at these notes on sequences again. So we have an arithmetic sequence like this, which means we're adding something each time. So to get from 3 to 7, well, we can subtract. 7 minus 3 is 4. So we're adding 4. Going from 7 to 11, you're going to be adding the same thing as if it's an arithmetic sequence. So we're adding 4 each time. You can just double check that. So to get to the next term, we take 15 and then we add 4 to it to give us 19. So 19 is the next term. So now we need to look at the nth term. So what I would recommend if you're trying to find the nth term in a sequence is writing out what you have. So our first term, we're given 4 terms here. So I'm going to write out first, second, third, fourth. So the reason I do this is because we want to find a general form for the nth term. So this essentially means we're going to plug in for the position, what number it is in the sequence, and then we're going to have a formula for that. I'm going to write this TH above so it's easier to read. Okay, so the first term is 3. The second term is 7. The third term is 11. And the fourth term is 15. So we need to be able to find a relationship between the number of the position and the number that's actually there. So corresponding 1 with 3 and 2 with 7 and 3 with 11. So there is a general formula for arithmetic sequences, but I don't blame you if you don't remember it just because we covered it in August, which was a long time ago. So things like this, you can kind of reason out even if you don't remember the general formula. Oh no, sorry about that. I have to share again. Sorry, I didn't touch my iPad and it fell asleep. Okay. So there is a general formula for arithmetic sequences, but because we didn't cover that, we covered it in August. That was a long time ago, so I don't blame you if you don't remember it. So we know that we're going to add 4 each time. So whenever we do this, it's kind of similar to our exponent rules where adding and multiplying have this correspondence. The same thing happens with sequences. When you add 4 each time, that's going to correspond with multiplying by 4 in your formula. So we're going to multiply by 4 and start here, right? So if you add 4 each time, you're going to be multiplying by 4 in your general formula. But let's see what happens. It can't just be 4n, right? Because we know that the first term is 3, where if we just multiplied by 4, the first term would be 4. But if we plug in n equals 1 and get 4, how do we get to 3? Well, to go from 4 to 3, we subtract 1. And then we can see if that works for all of them, right? So we multiply 2 by 4 and we get 8, subtract 1, we do get 7, it works. 3 times 4 is 12, we subtract 1 and get 11, so that works. And then 4 times 4 is 16, minus 5 is 15, so that works. So this means that our general formula is going to be 4n minus 1. So whenever you're adding a specific thing, it's going to correspond to multiplying that in by that number. We have a similar correspondence for geometric sequences where multiplying is going to correspond to raising something to a power. So it would be 4 to the n instead of 4 times n. Yeah. So then we want to use this formula to state the 20th term in the sequence. So the reason we have a general formula is because we can plug in any number term. So we just plug in n equals 20. So we do 4 times 20 minus 1. Remember that we multiply first. So that's going to be 80 minus 1, which is 79. Okay, so that's how you do these sequences. So this one was just a very slight bit harder than the one that we did in the other review. So are there any questions about sequences?
On part B, so is that like the best strategy? Like it's just sort of guess and check there, or what would you recommend?
Yeah, so I think probably the easiest thing to do is to know what the general formula is. So that's, oh, sorry, it timed out again. So I do think the easiest thing to do is to know the general formula, but there's already a lot that you have to remember for this final. So I think, yeah, the easiest thing if you don't want to go back and memorize formulas is to just say, I know that adding corresponds to multiplying, and then I see how that first term is shifted. We know that 3 is 4 minus 1. So you can shift it and then see if it'll work. And this process will typically always work. There shouldn't be anything more complicated than just adjusting it by a little bit. Any other questions on this one?
And then on the previous question, are we potentially going to be asked to divide whole numbers using an array? That's sort of similar, right?
Yeah, it is similar. So I think that I'm going to go ahead and say no to using an array.
Because that was on page 110.
Yeah, of the textbook.
Yeah.
Yeah, so there are a lot of models. However, I think that because there's just so much that I know that you have to remember what it looks like for this exam, that I'm going to say you won't have to divide whole numbers using an array. Anything else before the next one? Okay, so the next question from exam 1 version 2 is number 9. So this one is finding the area using a picture. So this one is essentially an area model question. So this dividing 15 by 6 using a partition model told you to use a particular model. It's specifically the partition model. So if you're told to find the area, so find the area and draw a picture, this tells you to use an area model, right? So find area using a picture. Another word for picture in math is model. So we're going to use an area model. So these can look slightly different depending on what you're doing. So there's different ways to draw area models, but I think the easiest one that we have the most exposure to, so sorry, it happened again. So I think the easiest one that we have the most exposure to is the area model using base blocks. It's probably the easiest way to do it. Okay, so if we use an area model using base blocks, so 23 is 2 longs and 3 units, and 11 is 1 long and 1 unit. So because of it's going to be a rectangle, right? So I'm going to do my 11 here on this side because it makes more sense with the space I have on the paper right here. So that's 11, 1 long and 1 unit. And then I'm going to have 23 here on the top. So I put a little multiplication symbol there. You don't have to. It just makes it easier so you know what you're doing. So that's 2 longs and 3 units. Okay, and that's 23. You also don't have to label these sides. It just makes it easier to see what's going on. Okay, so whenever we multiply using base blocks, so I'm also choosing to answer this question using an area model, using a base block area model, in case you, just to kind of cover what a base block model looks like with multiplication again. Okay, so remember, whenever we multiply 2 longs, we get a flat. And so you can think of this as essentially length times width, because base blocks are represented by these geometric shapes that, right? So assuming this is base 10, because if a number doesn't have a base written, you can always assume that it's base 10. So if you think about these longs are 10 by 1 blocks, if you watch the videos about what base blocks actually look like physically in like real classroom settings, it's a 10 by 1. It's a 10 by 1 rectangle, right? So you can think about that 10 as the length and another 10 as the width. So a 10 here is going to be the length of our shape, and the 10 here is going to be the width of our shape. And so we get this 10 by 10 square. And we're going to have that twice because we have another long here. And then we have a long times a unit, right, is going to be a 10 by 1 times a 1 by 1. So units keep everything the same. It's just kind of the easiest way to know what that does, right? Units represent 1, multiplying anything by 1 because 1 is our multiplicative multiplicative identity, keeps everything the same. So these units don't change the shapes that are above them. Then a unit times a unit is a unit. Sorry, these aren't the best little squares. Okay, so then we can add up everything that we have. So we have 2 flats, 5 longs, and 3 units. And there's no regrouping that we can do here, right? Because these numbers don't have bases listed. We're assuming that they're base 10. So we don't have 10 of anything that we can regroup. So we can see that 23 inches times 11 inches gives us flats are in the hundreds place, longs are in the tens place, and units are in the ones place. Gives us 253 square inches. Okay, so an area model that a lot of people did, it was kind of hard to draw for me, at least. Essentially, they drew like 11 rows and 23 columns. But I personally don't think that area model is helpful to actually solve this problem, right? Because if you do an area model like that, you just have to count you have to count 253 squares to get your answer. Whereas if you see, we have 2 flats, 5 longs, and 3 units, you can easily take the shapes that you have from your model and write down the answer. Remember that the whole point of using model is to help you solve the question. So just drawing 253 little boxes doesn't make the problem any easier. Whereas doing the space block model, I think very much does make the problem easier to see exactly what the answer is going to be. Okay, any questions on area models or models with whole numbers? Okay, so next we're going to go to exam 2, version 1, sorry. So exam 2, version 1. So we had these, right? Oh, this is the start of the questions that just said, here's a list of things and simplify it. Okay, so this one is really commonly missed. All 3 of these for number 2 were very commonly missed. And it's because of the way people have learned PEMDAS historically. So if we're looking at PEMDAS, I know I've said this in every review video, but I'm going to say it again, that multiplication and division are grouped together and addition and subtraction are grouped together. And we multiply and divide going left to right, and we add and subtract going left to right. Okay. So this is one thing that's a flaw in the PEMDAS. Oh, what is that called? Acronym, maybe? Where the letters mean something different. That's the flaw in this mnemonic device that we have. That's PEMDAS, parentheses, exponents, multiplication, division, addition, subtraction, right? These letters have an order. And a lot of times people think, oh, multiplication and then division, but that's not the way the algorithm works. So if you recall from the lecture videos, this is a convention that people chose. We have chosen to have multiplication and division grouped together going left to right. And that's the way that all math works, simply because we chose it a very long time ago. And we did a little exploration of what would happen if we did the algorithm differently, but this is the algorithm that we have. So we'll use it. So in the first one, we have only multiplication and division. So this one has only multiplication and division. So this one only has multiplication and division. So that means we're just going to go left to right. Okay, so if we go left to right, that means we're going to do division first. So if we start dividing 24 by 4, we're going to get 6. And then we're going to multiply by 3 to get 18. Okay, so that's all you do. So a lot of times, this more so happened on exam 3, where if you didn't do left to right, then you got something that didn't work out. So in this case, if you had done multiplication first, you would have had then your question would have been 24 divided by 12, which is 2. And it would have worked out. But on a lot of the questions on exam 3, if you didn't do the operations in the right order, then you had to divide something that wasn't easy to divide. And like I said in the review video yesterday, if a question seems like it's really hard to do without a calculator, you're likely making an error. There's probably an easier way to do it, essentially. And so that is what happened a lot on questions like these if you didn't do the operations in the right order. Okay, so the next one only has addition and subtraction. So we have 12 minus 7 plus 3. So this is only addition and subtraction. So that means that, again, we go left to right. So we're going to start out doing 12 minus 7. So 12 minus 7 is 5, and then we're going to add 3 to get 8. So this one has a more clear way to see why it's wrong to do the other way. So let's pretend that you are insisting on doing addition first, even though you know it's wrong. So if we do addition first, we would do 12 minus 7 plus 3. Well, I'm actually going to write this in red, just to kind of emphasize that this is the wrong way to do it. So 12 minus 7 plus 3. If you add 7 and 3 first, you're going to get 12 minus 10, right? And so what you're essentially doing is putting parentheses around this operation because you're doing it first. I don't know if you have seen this before, but if you put parentheses around the operation that you're going to do first, it doesn't change the problem, right? So if I had put parentheses here, it's the exact same because you divide first. And that's why whenever we write, so up here, when we write things in expanded form right here, you can put parentheses around the multiplication, but it doesn't change the answer because you're going to multiply first in the order of operations. So having the parentheses is the exact same as not having the parentheses in this case because you multiply first. So if we say down here, oops, that we're going to add first, well, that's essentially like putting parentheses around the 7 plus 3, right? If we're insisting that we're going to add first. And we know that we have the distributive property. So we can distribute the negative to the 7 and the 3. Remember that we can distribute multiplication and, we can distribute addition and subtraction, right? We have these distributive properties for our 4 basic operations. So when we distribute that negative sign, this is 4 minus 7 minus 3, because the negative goes to the 7 and that negative goes to the 3, right? So if you distribute that, this is 12 minus 7 minus 3. You change the question, right? And instead of adding 3 here, this operation is like you're subtracting 3. And so this is going to be 12 minus 7 is 5 minus 3, which is 2. It's not 5 plus 3, which is 8. So if you insist on adding first, it's like putting the parentheses around, which is like distributing the negative sign to the 3 and changing the question. So that's another way to see that it's not going to give you the same answer because of this distribution. And you can do something similar with the division. It's just may not be as clear because we don't distribute like that typically. Okay, so then part C. This was also commonly missed because of a lack of parentheses that a lot of people assumed was there. So PEMDAS, right? We do parentheses and then exponents. There's no parentheses in this question, so we're just doing the exponent first. So when we do this exponent first, we are squaring 2. We are not squaring negative 2. So this is minus 2 squared. So the minus is applied to the 2 squared. So this is going to give us minus 4 plus 4, which is just going to be 0. So a lot of people took this minus 2 squared as if we were squaring negative 2, but that looks different. So if we're squaring negative 2, it's always going to look like this. And that's going to give us 4. But if we're just looking at the opposite, right? If we're looking at negative 2 squared, we're just taking the opposite. Remember when we talked later, chapter 8, 7, something like that. In the last 3 chapters, we started talking about integers and their opposites. So this is just saying we're taking the opposite of 2 squared, which 2 squared is 4. We're taking the opposite, so that's negative 4. So there is something like this on exam 2 and 3 that you may have seen it in either place, but we're not squaring the negative 2 because there aren't parentheses around the negative 2. We're squaring the 2 and putting a negative sign in front of it. So all 3 of these were commonly missed because a lot of people messed up the left to right and or the negative 2 squared. So are there any questions on simplifying these 3 or simplifying in general?
On 2A, if you put the parentheses around the 4 and the 3, you said you cannot distribute the division sign because that's not a property, but I guess you would just do the parentheses first because of PEMDAS and get 24 divided by 12 is 2.
Yes.
Okay.
Mm-hmm.
Okay, thank you.
Okay, so there's a question in the chat. The negative always goes after the exponent. Okay, I think what you're asking is in the order of operations. So in this case, yes, because this negative sign in front of 2 squared you can rewrite this as a negative in front of anything can be thought of as multiplication by -1. So this is really -1 times 2 squared. And in our order of operations, the exponent comes first. So we evaluate the exponent. So this is -1 times 4, which is -4. So yeah, if it helps you to think of this negative as multiplication by -1, then it would come after evaluating the exponent. Yeah, that's a really good question. And I think it's a really good way to think about things like this if it confuses you. Any other questions on these? Okay. So the next question on this exam. So I pulled 3 questions from exams 2 and 3. Yeah. So the next question was to shade 2/3 of the following region. So it's very clear who watched the review video and who didn't, because if you watched the review video, I feel like maybe this exact question was on the review, but something very similar. So if you watched the review video for exam 2, it's highly likely that you knew how to do this. So if we want to shade 2/3 of the following region, so given this region, there's different ways to do it. So this is a half, right? So if we're just looking at the rectangles of this shape, this is a half. Oops, sorry. So this is a half, and that's a half, right? So where you're dividing it into halves here, right? We have one rectangle on top and one rectangle on bottom. Okay. But then each of those halves are broken up into more pieces. So there's kind of an implied, you can analyze the shape using multiplication of fractions, but we'll focus in on this top half. So we take this top half and we cut it in half again, right? So we have half here and half here, right? So a half of a half is a fourth, right? That's something that we all know, is that we have fourths here, okay? But what's happening? I don't know if I can even divided our top half into 2 other halves. So we have a fourth on top and a fourth, there we go, on bottom. Sorry, 2 fourths next to each other. So then we take this other half and we divided it, instead of halves, into thirds. So we have a third, and a third. So we have thirds of halves, which we know is 6. So this is 1/6 of the shape each time, right? So, I mean, this drawing that I have of the halves and the thirds, this looks really, really similar to the pictures we had on the lecture videos of multiplying fractions. Whenever we learned the algorithm to multiply fractions, we used a lot of pictures that look like this to kind of visualize. And the example we had in the videos was 1/6. So this should look really familiar. If we have a half and a third, then that's a half of a third is 1/6 of the shape, right? It's a piece of a part of a whole. Okay, so if we want to shade 2/3 of this region, so you can do it this way that I've done. So I know I didn't do it this way in the exam 2 review, but I'm doing it now just to kind of review how to take fractions of fractions. So we have fourths and 6. So we want to get 2/3 and we have all of these pieces. So what can we do? Well, that's a good question. So you can try and combine these fourths and these sixths to get 2/3. So the common denominator here, if we want to make it into a common denominator is going to be 12, right? So 2/3 is times 4/4, 8/12. So this is going to be 8/12. So 1/4 is going to be times 3 over 3, 3/12 of the shape. A fourth is going to be another 3/12 of the shape. 1/6 is each going to be 2/12. So we make those quarters and sixths into 12ths. You can make the shape into 12 pieces. I'll do that beside it. So if we want to make the shape into 12 pieces, yeah, that's perfectly fine. So because we already have it divided into halves on top and bottom, we're going to have 6 pieces on the top and 6 pieces on the bottom. So first I'm just going to draw what's there. So that's half, and then these thirds. So if we want to make the top and the bottom into 6 pieces, these halves go into thirds, and the thirds go into halves. So we have these 12 pieces. So what you can make the shape, whole shape into 12 pieces, and then piece it together to have 8 of them. So that's pretty simple, right? You're just going to take 8 of them. So you're just going to take 8 of these 12ths. An equivalent way to do that, using the 3, and the 2, the 3/12 and the 2/12, figuring out a way to combine them, we can take this 3/12 here, 3/12 here, so that's 6/12, and then combine it with the 2/12 down here. So that's also 8/12, so that's 2/3. So this is one way to do it, is to just kind of make it all in 12ths, is one way to do it. So there's another way to do it, which is the way that I did it on the review, is to just take the shape you're given and say, okay, so this bottom part is already split into thirds. So I'm just going to extend those thirds upward. So now I have the whole shape divided into thirds, and I'm just going to shade 1 of them, 2 of them. So that's also 2/3. And it's essentially exactly what we did on the right of the shape in red, just quicker, essentially. But yeah, this extending up thing is something that not a lot of people, well, I shouldn't say that. This extending up thing is something that a good amount of people forgot that you could do this. But if you don't like it, you can just split the whole thing into 12ths, and then we just shaded equivalent regions. Okay, but the point of this question was to take a shape that was divided into fourths and sixths and somehow combine that into 2/3. So there are multiple ways to do it. I just showed you 3 of them. So are there any questions about shading pieces of regions using equivalent fractions?
The one on the left, what's the reasoning behind that? Did you mean to draw a bar on the second one to make it 6 pieces on the bottom, or are you just showing that? Because I think I see you have like just 3 squares on the bottom with that blue one.
So with the blue one, yeah, you do only have 3 squares on the bottom. So what I did in this one was like so. So I see that the bottom is already dividing the shape into thirds. So I can just continue this line up and continue this line up to say that if I look at it, this box is 1/3 of the shape. This box, if I drew them equally, it would be 1/3 of the shape, and this box is 1/3 of the shape. So you essentially extend the bottom lines up so that you divide your shape into thirds vertically, right? Our shape's already divided into halves horizontally, but we can extend the lines up to have the shape divided into thirds vertically. And then, well, each of those vertical rectangles is 1/3, so I'm just going to shade 2 of them.
And which method do you think is the best to show students first?
Well, I think that this kind of dividing thing, I think the right-hand side is probably easiest for students to grasp first, is to just kind of take that a shape is divided into fourths and sixths, and then to just kind of make it into 12ths using a common denominator. I think that the method on the left is probably a little bit harder to extend it up and ignore lines.
Yeah. And then when we say 2/3 equals 8/12, I know you said you didn't want us to do a cross multiply, so we just can say multiply by 4 on top and bottom, or would you even need us to show that work? Or?
No, yeah, you don't have to show that work. You just, yeah, multiply by 4 on top and bottom.
Okay, thank you.
Mm-hmm. Okay, so the last one is ordering fractions using a number line and benchmarks. So this was also a commonly missed question. Because of this instruction, I know I mentioned this in the last review video, but use a number line and benchmarks. Okay, there were some people who got points off because they converted everything to decimals. So at this point in the semester, we hadn't even talked about decimals. So definitely converting things to decimals was not the way to go here. Especially 12ths is not a common decimal to just know on the top of your head. Okay, so what do we do first? So whenever we talked about this earlier in the semester, one thing that we identified was what was closest to 0, 1/2, and 1. And those are the benchmarks that I'm talking about. So what is closest to 1/2, closest to 0, and closest to 1. So that essentially amounts to finding the smallest fraction in the list, the largest fraction in the list, and then the one in the middle. So I don't know if it's abundantly clear just by looking at these, which one's closest to 0. Well, maybe it is. So if you look at these a bit, we can see that 3 of them are 12ths. And so out of the 3 12ths, right, so 3 12ths, 5 12ths, and 7 12ths, so the 3 fractions with a denominator of 12, we can clearly see that 3 12ths is the smallest out of 3 12ths, 5 12ths, and 7 12ths. But then 3 12ths, we know we can say that it's 1/4. And so that one is pretty clearly smaller than 2/3 and 5/6. So the 3 12ths is going to be our closest to 0. Then we can also see which one is closest to 1. There was a part in the lecture videos where we compared fractions if we added one to the numerator and the denominator. Because you may look at this and say, yeah, I really don't know which one is biggest, but if you look at this 5/6, 5/6 is going to be the one that's closest to 1. Because 5/6 is equal to 10 12ths, which is definitely bigger than 7 12ths. And then 2/3 is equal to 4/6, which is definitely smaller than 5/6. So 5/6 is going to be the biggest fraction here. And then we can also see what's closest to 1/2. Oh, sorry. I should write that closer. We can also see what's closest to 1/2, because what's closest to 1/2 is going to be 5 12ths and 7 12ths, right? Because 1/2 is 6 12ths, and these are each 1/12 away, right? They're closer to 1/2 than 2/3 is, because 2/3 is 8 12ths. Okay, so we can see that we have these things using the benchmark. So let's go ahead and place them on a number line. So we have 0, 1/2, and 1. I should probably put the 1/2 in the middle. 0, 1/2, and 1. So closest to 0 is going to be 3 12ths. Closest to 1 is going to be 5/6, and then around 1/2 is going to be 5 12ths and 7 12ths. So by using these benchmarks, we've already placed 4 of the fractions. So 5/6, 5 12ths, 3 12ths, and 7 12ths. So we just need to know where 2/3 goes. So 2/3 is definitely going to be bigger than 1/2, right? So we need to now see where it goes. Is it going to go here, here, or here, right? Because it's between 1/2 and 1, right? It's less than 1. Okay, so now we're going to compare it to 7/12 and to 5/6. So 2/3. If we're comparing it to 7/12, we can make it have a common denominator of 12. So we multiply by 4 on top and bottom. So this is 8/12, which is definitely bigger than 7/12. So it's not going to go here. And then we already said that 5/6 was the closest to 1, but we can go ahead and check it again. So we see that 2/3 is 4/6, multiplying on top and bottom by 2, which is less than 5/6. So that means it's going to go right here. So 2/3 goes here. Okay. So I know I said a strategy that some people did was converting everything to decimals, which when you're just ordering fractions is not the way to go, right? Because it tells you to use other methods. But some people drew a weird pie graph thing. So they drew, right, and said like 5/6. Ooh. They said like 5/6. Oh, sorry, I can make 6 maybe. Yeah, it's better. So they said, yeah, 5/6 is this much, and it's bigger than, right, 2/3 is this much. So 5/6 is bigger than 2/3. Even though this is correct drawings and a correct comparison, it doesn't use the number line, right? And so the whole point of this question was to use the number line. So even though this is correct, there were a decent amount of people who did this, which kind of confused me. I didn't really know where it came from. But yeah, use the number line if it tells you. I don't know if you've gathered something. I did. Do it. Okay. So are there any questions on ordering fractions?
With the 2/3, so are we just so did you just put it like, is it okay if it's like, it looks like you put it exactly halfway between the 7/12 and the 5/6? Is that gonna be like acceptable? Because you know it's like less than 1 and greater than the other.
Yeah, this doesn't have to be perfectly to scale. So another way that so this corresponding question on the second version of exam 2, you'll see on the answer key, I just converted everything to have a common denominator, which you could have done that here. You could have converted everything to have a common denominator of 12 and like place things exactly where they went on the number line, but there's no need to do that as long as they're in the correct order. So yeah, placing them smallest to largest. I guess I probably should actually also write out the list of them in order from least to greatest, 2/3, 5/6, right? So this is the order that they're in. Mm-hmm. Any other questions? Okay, so it's almost 3:30 and we just finished one of the exams. So we've gone through 3 of the old exams, commonly missed questions. So we'll go through the other 3 tomorrow at noon. So I'm going to go ahead and stop the recording.